All right, good morning, everybody. Let's go ahead and get started. If we could quietly reach an end to your conversation, which I guess doesn't matter. Yeah. Oh, all right. So, couple of things. I have a number of demos today. It's Monday. How are we doing? So I've got these two devices here, and we can see there's a wheel, and it's a free spinning wheel, and it's not doing anything unless I push it. We agree? Right? And I have two identical ones. Okay? I'm going to put one of them on top of some liquid nitrogen. And the other one, if I can get hot water to boil, I will put it on hot water. All right? These are called Stirling engines. Has anybody heard of a Stirling engine before? Number of you? Okay. All right, so one side of this is at room temperature. The other side's liquid nitrogen temperature. And liquid nitrogen is characterized as particularly cold. All right, and while the water's boiling, I'll talk about some other things. So exam 3 is coming up. This Friday there'll be a review session. Brian's going to facilitate that. Sunday there'll be another one. Study materials are posted. So last time we met, we've talked about isolated systems not being at equilibrium. If I'm not at equilibrium, we know that the system's going to move in the direction to achieve equilibrium. That's accompanied by an increase in entropy, and the entropy is going to keep increasing until equilibrium is reached. At equilibrium, we're at the maximum entropy for that system, and there's no longer any change. Right? We've pointed out that if I have a reversible process, it's at equilibrium every step of the way, and therefore ds, or delta S, for that reversible process is equal to 0. Right? Then we talked about systems where we allow interactions with the surroundings, right, with regards to heat exchange. So whether I have an isolated system or not, ds is greater than or equal to dq over t. That's called the inequality of Clausius. This is a statement of the second law. Right? From there, what we did was we explored the statistical thermodynamics point of view of entropy, S equals kV ln W. We showed that it behaves the way we expect. So if I have perfect order, all of my systems in the ensemble in the same quantum state, I am at natural log of 1. So entropy is equal to 0. That also has implications down the road. If I have a perfect system, everything ordered and aligned, that means that its entropy is going to be 0. We have an absolute value of entropy in that case. Right? We also saw that because of the nature of the natural log of W, that we can treat entropy as an extensive property. That is, we can add the entropies of the components of a system to make up the total entropy. All right? And then we said that when we're at equilibrium, we expect our systems in our ensemble to be distributed over all of the possible quantum states equally. Right? So that's like saying, you know, I have a dice. Right? And if I roll it 1 billion times, you expect to see 1/6 of those with 1 on it, 1/6 of those with 2 on it, 1/6 of those with 3 on it, right? So at equilibrium, we can say that we are everybody, all the groups are equally populated. And under those circumstances, we derived this expression that said that for a single system, the entropy is given by kV ln omega, where that's the degeneracy of that system. Okay? All right. And there'll be some homework coming up that explores that a little bit more. And then we also showed that we could calculate the degeneracy. We didn't derive this. Constant depends on the number of particles. A function that depends only on the energy and then the volume to the number of particles. And this is specifically for an ideal gas. Using this relationship, we were able to show that, as we expect, delta S for isothermal expansion is given by nR ln V2 over V1. All right. I think I have boiling water. Let's see. Get that going. Put that there. All right. And let's see. We got something going on there. All right. So it looks like I'm getting what I want to do. Okay. So let's talk a little bit about this, and this is foreshadowing some things that we'll either get to today or on Wednesday. But what we can clearly see that with that Stirling engine is that it is moving, right? And all I did was I just needed to get it a little bit of a push start, all right? But it's moving, and whenever I had the top plate and the bottom plate at the same temperature, I push it and it stops, right? So this is saying that there's heat transfer that's driving this process. You agree? Right? So in this case, if you think about a heat engine, you know, like an automobile or something, you have to put heat into it, and some heat has to leave. Where's the heat source going in this case? It's the room, right? And then some heat's being deposited into the cold reservoir, all right? So I don't know if this is equilibrated yet. It takes a little time. Oh, that looks like that's going too. All right. Let me stop, make sure. Yeah, it's definitely going, all right? And then we can see for our, all right, I should be wearing gloves. Well, it's April Fool's Day, right? So I'm going to behave as a fool, all right? So in this case, I've got exactly the same model engine, correct? Right? Now where's my heat source? It's on the bottom, right? And that means that the cold source, or the cold sink, is the room, right? And so this clearly demonstrates that the only thing that's important to get this thing operating is a difference in temperature between the top plate and the bottom plate, right? We're going to see that's going to be pretty important. I can watch these things for hours. I don't know why. There's something wrong with me. Okay. All right, we have another demo. So when it looks like most of you are falling asleep, that's when we'll do the other demo. And the nasty part of it is I'm not going to bother waking you up for it. Just kidding. All right, so questions today. We're going to be using this, you know, the thermodynamics results for statistical thermal, talk about the mixing of an ideal gas, for isothermal process. And if you think about it, if I have two gases, both at the same temperature, separated, little valve between the two, I open the valve, what do you expect to have happen? It's going to equilibrate. You're going to get a mixture of those two, right? Okay. And we've already pointed out that there's no change in the energy of that system because that's the spontaneous direction, going from isolated components of a mixture to uniform composition. That means we expect delta S to be positive for this process, and we'll show that that's true, right? We've talked about delta S of the universe for a reversible process. And what we've shown, and we'll review that today, is that delta S for our system, if it's done reversibly, is going to be the same as delta S for the surroundings, but the opposite sign. And that gives us a delta S of the universe equal to 0. Right? That's for a reversible process. We also know under most circumstances, most processes are not reversible, and so we have to talk about what we, you know, how we handle non-reversible situations. Right? We'll also talk about delta S of mixing of ideal gases from the classical thermodynamics point of view. So we'll do it at statistical thermal and then classical thermal, and then we'll talk about the heat engine a little bit further. Okay? All right, some things that we're going to be needing to use today, I think. If we have the same temperature and pressure for ideal gases, equal volumes of the gas have equal numbers of particles. We mentioned that last time. That's Avogadro's law, right? The implication that that has for us is I'm talking about the volume of one of my components over the total volume of the system. That's going to be the same as the number of moles of that component over the total number of moles. Does that make sense? So this directly falls from equal volumes of gas have equal number of particles. Okay? All right. Number of moles of one component over the total number of moles. What's that known as? That's a composition. It's not quite the molarity. Molarity is moles per liter. This is mole fraction. All right, so we're going to say this is Y1, and that's mole fraction. Right, so in this chapter and future chapters, we're going to be using the concept of mole fraction. So we expect Y1 to be greater than 0, right? Otherwise, they're not going to bother talking about it. And what's the maximum value for our mole fraction? It's going to be equal to 1, right? So our mole fractions go between 0 and 1, and they reflect the composition of our mixture, right? Back in Gen Chem, you probably used X or possibly chi to symbolize this. We're going to reserve Y for discussions of gas phase mole fractions. We'll use a different one when we're talking about liquid phase mole fractions. Okay, so starting into some new material, right? So here's the situation. We've got gas 1, gas 2, separated, same temperature on both sides. Don't care whether the number of particles are the same or not, but just the same temperature. I open the stopcock. We expect at equilibrium that we're going to have a mixture with the same composition on both sides. We want to get at delta S of mixing for this process, right? And so what we know is that this delta S will correspond to S of the mixture minus S for component 1 plus S for component 2, right? So this is S1, S2. That's going to be the entropy of my system before mixing has occurred. And then at the end of this, entropy corresponds to this, right? OK, so now what we can do is we can substitute in the relationship that we derived last time, Kb ln omega for the final state minus Kb ln omega for component 1 minus Kb ln degeneracy for component 2, right? And I can simplify this by saying that delta S of mixing is Kb ln omega mixing over omega 1 omega 2, okay? Because I've got Kb in front of these natural logs. So that becomes a natural log of this minus that. All right? So I can combine that into a single fraction. All right, and previously what we've said, the degeneracy is given by a constant that depends on the number of particles. So that's going to be Cn1. A function that depends on the temperature or the energy of component 1. And then the last term that we need to consider is the volume. In this case, it's volume 1 raised to the n1 power, right? Because clearly, initially, component 1 is limited to that volume. We write the same thing for omega 2, right? So for omega 2, degeneracy of component 2, that's going to be a constant depending on the number of particles for 2, a function of the energy of those particles. So that's going to be E2, and then V2 raised to the N2. Okay? All right, then the other thing that we need to do is talk about the degeneracy for our mixture. All right? And for our mixture, what we need to remind ourselves is we're talking about ideal gases. So ideal gases behave independently. So omega is related to how we can arrange the system, right? And so if I'm talking about omega of the mixture, that's going to be omega for particle 1 times omega for particle 2, because they're independent of each other. Okay? All right, and then omega 1 and omega 2 at the end of this are pretty similar to what they started out with. I still have the same number of particles of particle 1, same number of particles for particle 2. I have the same energy for particles 1 and the same energy for particle 2. But the big difference is, at the end of this, this isn't confined to V1. This is going to be in V1 plus V2. This was in V2. Now it's in V1 plus V2. So our total volume has changed. So this becomes V2 plus V1 raised to the N1. And then for my second particle, that will be V2 plus V1, or the total volume, raised to the N2. Right? And just for completeness, that would give me the degeneracy for 2 in the mixture. And this first portion will be the degeneracy for component 1 of my mixture. Make sense? Yeah. What's that? Is it driving you crazy? Should I? Or should we continue to drive him crazy? I'm just kidding. Okay? All right, so at this point, what we can do is we can plug those all in, right? And it looks a mess, but the thing that's nice about statistical thermodynamics is if you're doing everything correctly, a lot of things cancel, right? So this represents my mixture. That is what we've just written above. This represents the degeneracy for component 1 before we've done mixing, degeneracy for component 2 before we've done mixing. So we've got constant, constant, that cancels. Function of same energy, that cancels. Constant depending on number of particles for component 2. Energy of component 2, that function stays the same. And so I'm left with just the ratio of the volumes. Okay? All right. And that was just the that was just the ratio of our degeneracies. So we need to take the natural log of that. And that's what I've done below. All right? So I take the natural log of this times this. That's going to be the same as the natural log of this plus the natural log of that. So I've got N1 ln V1 over V2, or V1 plus V2 over V1. So that's from this first term, all right? And this is from the second term. That all make sense to everybody? Okay? All right. And then at this point, I'm going to flip. Instead of having the total volume on top, I'm going to put that on the bottom. And what that does is it introduces a negative sign out front. Okay? And because we've said that V1 over V1 plus V2 is the same as N1 over N1 plus N2, I can replace those, all right? And we know that N1 over N1 plus N2 is the same as the mole fraction. Okay? And so that says that the ratio of the number of moles of component 1 to the total number of moles, that's going to be mole fraction component 1. This will be mole fraction component 2. So that's what I've done down below. Okay? All right, because we're talking about delta S, now I need to reintroduce the Kb ln omegas, right? So I've got the Kb out front, N1, N2, right? And we know that Kb times N is going to be the same as minus Nr ln y1 minus N2R ln y2. That all make sense? Okay? All right, so we see that we've got 4 different variables. We can do further simplification, because if I take both sides of this and divide by the total number of moles, that gets rid of the number of moles of each of the components. So I will divide by N1 plus N2, right? That will get me the per mole entropy of mixing, right? And then I can say minus Y1 R ln Y1 minus Y2 R ln Y2. Okay? All right, so I've just done this for a 2-component mixture. I'm going to be a little sloppy and say we can generalize this to multiple components. Because what we see we've got going on here is mole fraction times R times natural log of the mole fraction. So if I have 10 components, I just have 10 terms that look like that. Okay? And so we can say in general, this will be minus R times the sum from I equals 1 number of components mole fraction of that component times ln times the natural log of the mole fraction. Okay? All right, now at the outset we said we expect this delta S to be greater than 0. All right? Well, let's see if that's what we expect. All right? So what we know is that yi is going to be less than 1 and greater than 0. All right? And so that tells me that the natural log of yi will be, help me out, is going to be negative, right? Right? And so that says that this term is always going to be negative. And then I've got a negative out front. So this is always positive. Okay? Therefore, minus r y I ln y I greater than 0. Okay? All right, so we've shown that delta S for mixing of an ideal gas is a positive quantity. Right? We expect it to occur. When we talk about perfect solutions, we're going to see we have exactly the same relationship. All right, now I have to go to notes for a moment. Okay, so when we're talking about our system, we need to use a reversible process to calculate delta S. And if you think about it, that's because if we go back to the inequality of Clausius, it's only an inequality if I have an irreversible process. If I want to know the exact value, I need to choose a reversible process, right? Okay, so, and we know that that's okay to use for our system calculation of delta S because we know that entropy is a state function. All right, so what we're going to do is we're going to talk about the difference now between a real irreversible process and the irreversible processes that we've discussed so far. And we're doing it thinking about an expansion of a gas isothermally into a vacuum, okay? Because if we open that stopcock, if P is equal to 0 over here, you expect it to go one way and one way only. You can't incrementally get it back to where it was, right? How many people have been on a plane whenever the window opens? Right? No way to get back in, okay? All right, well, anyways, that's what I think of when I think about going into a vacuum. All right, being sucked out the window of a plane. All right, so what we normally expect to have happen is this to irreversibly occur, right? And it happens rapidly, right? High pressure, zero pressure. And because it happens really rapidly, there's no time for adiabatic equilibrium to occur, right? We can't absorb any heat. Okay, so we know that we can calculate delta S for the system for the reversible process. Because if I start here and end here, it doesn't matter how I get between those two. If my temperature is the same here and here, those 2 points are all that matter, right? And we've talked previously about how we get there. So because it's isothermal and because it's an ideal gas, we know that delta U is equal to 0. Therefore, the heat transfer is equal to the amount of work, energy, right, but opposite in sign, right? And because of the definition of entropy, we can say that delta S for that process is the integral of dq reversible over T V1 over V2. I see I forgot an integral sign in there. All right, we end up with our NR ln V2 over V1. And for this process, if it's an expansion, V2 over V1 is greater than 1, and therefore the natural log is going to be a positive value. All right, let me put that in parentheses. V2 greater than V1. V2 over V1 is greater than 1. ln V2 over V1 is going to be greater than 0. Positive. Okay? Make sense? All right, so that's about the system itself, right? If I want to talk then about the interactions of the system with the surroundings, I can choose two ways to think about it. I can choose to do a reversible interaction with the surroundings, which we've previously discussed to some extent, or I can talk about an irreversible process, right? And the big thing is you need to really be careful about what's the system and what's the surroundings. Because what we've established is that whether I do this expansion reversibly or not, from the system point of view, if my beginning point and end point are the same, I can calculate that delta S using a reversible process. So the big difference occurs with the interactions with the surroundings. We have been determining delta S for the system up to this point. All right? Okay, so if I think about an isothermal process and I choose a route which is reversible, if I choose a reversible route globally, right, with regards to interactions between system and surroundings, then that tells me that delta S of the surroundings is going to be equal to minus dq reversible of the system over T. All right? And because that's just the negative of what we've started out with up above, then this all becomes minus nr ln v2 over v1. And we've previously talked about that. Okay? And that, of course, is equal to 0. All right? And that occurs if universally we're doing this as a reversible process. Right? And again, we connect that back to the idea that we're at equilibrium every step of the way, therefore we don't expect an entropy change. So now what we want to do is talk about what happens in reality. All right? So for our irreversible expansion, the process is isothermal for our system because the temperature ends up the same. Right? So we can say that the irreversible work is equal to minus the heat transfer for the irreversible process. Okay? And that's supposed to be down there, right? You gotta be kidding me. Are we out of time already? No. I have no idea what that is. Okay, I must have gone into a time warp. Did somebody get into my phone play an April Fool's joke on me? No. Okay. All right, so at any rate, okay, so then the thing that we need to think about a little bit is, under this example, we're going to a really, really low pressure. P external, it's vacuum, so it's equal to 0. Right? And if the external pressure is equal to 0, that tells me that my work is equal to 0. Right? And if you think about it, if I have no work, and delta U needs to be 0, that means I have no heat transfer either. Okay? Right? So in this case, this is going to be the integral of 0 over t, which will be equal to 0. Right? So this is saying that delta S for our surroundings is going to be equal to 0. And then the total for the system will be nr ln v2 over v1. That's delta S of the system plus 0. And that's going to get me nr ln v2 over v1. And that clearly is going to be greater than 0. Right? As we expect, I open the window of a plane, irreversibly, the air rushes out. And all the people fly away. Okay? Thank you for laughing. I know it's dark. All right. Okay? All right. So now recognize something. The reversible process represents one limit. We take forever to do it, and delta S of the universe is equal to 0. In this case, I'm at another limit, right? In this limit, I'm basically saying there's no exchange of heat with the surroundings. in reality, if I go back to this picture, unless this is, in an airplane out in space, I have a volume here. And as the gas comes through, I start to build up gas on this side, and the pressure starts not being 0 anymore. It starts going up, right? So all we can say is that for the real system, our delta S of the whole universe is going to be between these two limits. Does that make sense? Between 0 and that upper level, nr ln v2 over v1. Okay, so next up, what we want to do is we want to look at the entropy change for mixing of two ideal gases. And we've just done this using statistical thermodynamics. So we're going to do exactly the same thing, but now from the classical role, right? So the thing that we know is if we're going to assume that we have ideal gases, that means that the bromines don't care that they're next to nitrogen, etc. So really what we can think about this is bromine is expanding from V1 to V2, right? And nitrogen is expanding from V2 to V total. Okay? All right. So just to get some nomenclature down, VBr will be the volume of bromine. Vn will be the volume of nitrogen initially. That final volume will be VBr plus N. Okay? Makes sense? All right, and if we think about this as simply an expansion from V1 to V2, that tells me that delta SBr is going to be the number of moles of Br times R ln final volume over the initial volume. So the initial volume is VBr, and the final volume is VBr plus N. Okay? And I can write the same thing for delta S for the nitrogen. That'll be the number of moles of nitrogen, R ln VBr plus N over Vn. Okay? All right, so this is the entropy change for the nitrogen doing the expansion. This is entropy change for bromine doing the expansion. The total delta S is going to be the sum of those two. So we've got NBr, R ln VBr plus N over VBr plus N R ln VBr plus N over Vn. Okay? All right, now I want to do this in a single step. I recognize that this is my total volume, this is my initial volume. I can flip it, and if I flip it, that puts a minus sign in front, right? So let me just write ln minus ln Vn over VBr plus N is equal to ln V total over Vn. All right? So that means I'm going to be able to replace this with minus ln Vn over V total, and this minus ln V bromine over V total. Right? And because we know that we're at the same temperature for everything and the same pressure, we also can say that this is equal to minus ln N nitrogen over NBr plus N. Okay? And this is the mole fraction of nitrogen. Okay? All right, so that's all summarized in this term. All right? And then, of course, what we can do is divide by N total, and that tells me that my molar entropy on mixing is minus the mole fraction times R times the natural log of the mole fraction. And in general, it's going to be equals minus R summation I equals 1 number of components of yi ln yi. Right? And we've already seen this equation before. It's exactly what we saw for the for statistical thermodynamics. So for the same reasons, this is always positive because yi is greater than 0, less than 1, and the natural log of yi is going to be less than 1. Okay? Make sense? All right. Let's take a moment to do a demo. So this is one that I have alluded to previously. Ooh, somebody has a small head. Or maybe I have a big head. Giant head. All right, so I've got two solids that I'm going to mix. What do I want to do here? I'm going to be stupid, and I'm going to take the chance of damaging my thing. Do they feel like they're at room temperature to you? Room temperature. All right, so I have two solids. I've got a fancy thermometer known as a thermocouple. And right now, it says that the room looks like it's 22 degrees. All right, so I'm going to combine these two substances. All right, they're two solids, two reactants. I need to stir them around a little bit. Before I do that, I'm going to grab a cork, and I'm going to put a little bit of water on the cork. And we'll show why in a minute. All right. I'm not going to stir it with that. I'm going to stir it with this. Yeah. Oh, you don't see anything, do you? Oh. Huh. Somebody must have disconnected the document camera. That's all right. We've got a living person that can say 23 degrees. Okay. All right. 21. 20. So it's clearly going down, right?
17.
There. Right. And if you think about it, all I'm doing is stirring it. And if, in a normal circumstances, if I was just stirring something, what would you expect to have happen to the temperature? It would go up a little bit because I'm doing some work on the system, right? Where are we? Did we get negative yet? Okay. All right, so I will go ahead and pass this around. Do not inhale this directly. One thing that's given off is ammonia. Grab it at the top, but pretty clearly we can see that it's frozen onto the bottom, right? If this had been an exothermic reaction, what would have happened to the temperature? It would have increased. So the temperature went down. That tells me it's a endothermic reaction, which means it needed to absorb heat from the surroundings to go. And all I did was mix it, okay? So this is clearly a case where looking at energy changes alone are not sufficient to determine spontaneity, right? And you saw that I started with solids, and at this point, I've got, do you see any paper towels anywhere? Huh. I'll just lick it off. That was a joke. We're good. Okay? Oh, thank you. So I have a friend that's a physical chemist at the University of Iowa, and she basically became a chemist because she saw that demonstration in general chemistry and just thought it was the coolest thing, all right? Literally the coolest thing. All right. Let's go back to lecture. And could you give me another paper towel? Now we'll find out if I damaged my Surface Pro. Thanks. Okay, so next up, what we want to do is we want to talk about heat engines. Okay, so in this section, we're going to be talking about conversion of heat into work. Right? So heat engine's anything that takes heat and converts it into work. So your automobile, internal combustion engines, these Stirling engines, they're taking heat, they're converting them into work. Right? So what we saw in the example here, I needed to have a hot reservoir, I needed to have a cold reservoir. And some of the heat transfer is exchanged into work. All right? Does that make sense? So let's talk about this from the thermodynamic point of view. All right? So I'm going to look at a pressure versus volume curve. So I have pressure, I have volume. And let's choose an isothermal path. Okay? So if I choose to go from point 1 to point 2 isothermally, we know that delta U for that step is equal to, it's equal to 0 because we're not changing the temperature. And then the heat transfer is equal to the work transferred, but the opposite sign, right? The other thing that we know is that in going from 1 to 2, we're expanding. That means we're doing work on the surroundings. And graphically, that's going to be the area under this curve, right? So work reversible will equal nRT ln V2 over V1, right? And it's negative because we're doing work. Okay? Does that make sense? All right. Now let's ask this question. Let's say this is our engine, right? So I go from 1 to 2. And let's say I go back to 1 and back to 2. And that's my cyclic engine. What's going to be wrong with my engine? Going from here to here, I've done this much work. What do I have to do to get from here to here? The same amount of work, right? So there's no way for me to get a net work output by following the same path. Okay? But if somehow I can get down to another isotherm, 2 down to here, then I come back here and come up there, and I've got some net work. Does that make sense? Right? So for, just thought processes, we're going to choose to go from here to here via an adiabatic path. So Q is equal to 0. Okay? From 2 to 3. Right? And then what we're going to do is we're going to take our engine and we're going to go back along an isothermal path. Right? And we can say all the same things. Delta U is equal to 0, Q is equal to minus work reversible. But in this case, this is going to be Q reversible for our cold sink, right? Because it's clearly at a different temperature. And that's going to be equal to minus W reversible for the cold path, which would be nRT ln V2 over V1. Okay. And then, of course, because we want our engine to operate cyclically, I need to get from my isotherm back to my starting point, right? And so in this case, we're going to choose, again, an adiabatic path. Which means Q equals 0, right? So now, without thinking deeply about anything, if I travel back and forth on the same path, I don't get net work. if my goal is to get a lot of work out of the system, what are you going to do about the isotherm, this isotherm? You're going to choose to operate at what kind of temperatures? You want the biggest separation between them, right? So it's going to be the lowest temperature possible, right? Does that make sense? All right, we'll pick up there next time. Have a good afternoon.